Good afternoon, everyone. Welcome to the end-to-end encryption, a double-edged sword. But Nalini Elkins from Inside Policy will be chatting to us. Nalini, do you want to start off?
Okay, perfect. Let's go ahead and get started. So this is a story of armed conflict. And it's conflict in a number of different senses. As you know, of course, the reason we have encryption is because there is an ongoing war between people who wish to do us ill, that is to do fraud and get your bank account number, credit card number, so on, and help themselves to your money, and so forth. There is also conflict between two different camps of the quote unquote good guys. And this is the conflict between privacy advocates and people who want to manage their networks. And both sides are right, but this has been the story of the encryption battles for the last, at least the last 6 years that I have been involved with them at the IETF. And people do not seem to understand history very well, which is to say that if you don't leave people, if there's a market for something, let's put it this way, if there's a market for something, there will become a black market. So for example, drugs, right? Why is there a black market for drugs? Because there's a market. And so you have to think, what can we do to satisfy this? And how does this apply to encryption? Well, both sides of this particular battle are right. Both the privacy advocates who want to encrypt all data, as well as those people who want to manage networks. And probably all of us on this call are probably in the want to manage our networks column, although of course we don't want people reading our emails and getting our data and tracking us. So on a personal level, we have those concerns too, as well, of course. We don't want private data divulged about our customers. So anyway, there are both points of view, and both sides are right. We have to think of how we can come to a meeting of the minds around all this. And as I say, this has been the battle primarily taking place at the IETF for the last 6 years, and it continues. So let's think about what we all agree on. Encryption is about hiding what we don't want bad folks to see. Of course, the devil is in the details here. Who exactly are the bad guys? And what is the thing that we want to hide? Probably we can agree on some very, very clear cases. For example, we can agree that people should not be able to see our credit card numbers. But exactly how are we going to do that? And that's a very difficult question. And if you hide the credit card number from the person who's trying to diagnose a system problem or the application developer, it becomes very hard to manage your networks or find bugs. So it's a tricky issue. So let's take a very clear example. Let's talk about 3 different protocols. The primary one I'm going to talk about is TLS, or Transport Layer Security. You may also know this as SSL, Secure Sockets Layer. When it was standardized at the IETF, it became TLS. It is the most widely used security protocol in the world, and it is standardized at the IETF. One of the newer ones is DNS over HTTPS. Clearly, when you do DNS, there is a great deal of data passing in the clear about what websites you're going to, who you are, and so on. And that is probably not something you want everyone to see. There have been multiple efforts to encrypt this data. The one that seems most likely to succeed at this point, although this is in flux, is DNS over HTTPS. Hence, all of the DNS is encrypted. DNS over HTTPS embeds TLS in it, and in yes, and so then we're back to TLS. Quick. This was also known as Speedy, SPDY, when it was with Google. Google brought it into the IETF. It is the new transport layer, equivalent to TCP or UDP. And the point of Quick is also to encrypt not just the payload, but the transport header. The transport header, for example, in TCP contains the sequence and ACK numbers. So you know how the transaction has proceeded. And again, certainly all well and good to encrypt things, but this makes network management quite difficult. Quick also embeds TLS inside of it. So again, we get back to TLS. So we have 2 points of view. The privacy advocates who say everything should be encrypted. And this is not to say in any way that they're wrong. There are governments who monitor their citizens and will squash dissent. And of course, they have their own point of view in doing that. And of course, each government is entitled to do whatever it likes. But people feel that dissidents should have a point of view. And of course, that is, well, for most people, not an argument, certainly. But then when you have the large brick and mortar enterprises, and by large brick and mortar enterprises, I will show you examples. I really mean the entire financial and governmental systems of the world. Most of them, if not all, use networks, and most of them have large private networks, large private internets that they operate. They do not just go to the public internet. And network management, fraud detection is crucial to these large enterprises. And we'll talk about exactly why in a moment. So let's take a one-line change done about 6 years ago. And what that one-line change was in the very initial drafts of TLS 1.3. And what it did was to remove support for static RSA and Diffie-Hellman key exchange. The key word here being static. Static. This one line is the cause of a major battle. In fact, I was unfortunately quite involved in this battle. It requires an enormous restructuring if you take static RSA away, and I will explain. So this is an internet draft, and you can look at it. It has since expired. It was from one of the Cisco fellows, Nancy Cam Wingate, who works at Cisco. And what she said is that if you remove static RSA, you cannot share the static key with the middle box, which means that the middle box cannot decrypt the data. And that is network monitoring, troubleshooting, compliance, and so on. This is only one example of a draft and the battle which went on. And to go back to what I said in the beginning is that if you disallow people from doing network monitoring, troubleshooting, and compliance, will they go along with it? Hardly likely, right? What you want to do is create an optimal method for them to do it. Otherwise, the choices they make will be, as we say, suboptimal. So I am not saying they are wrong to take away RSA. RSA is very fragile. You may wish to listen to my talk on the quantum computing and post-quantum crypto suites that I did yesterday, where I go into a great deal of detail about how quantum computing can be expected to break RSA in the near future. And I will go through a few slides on that, but there are other things also. RSA depends on prime number factorization, which initially people thought could be broken only with brute force. So there are some other things now. There is what is called a robot, or return of Blindbacher's oracle threat. This is a long-term vulnerability which allows getting RSA decryption and signing operations with the private key. People thought that Blindbacher's oracle threat was no longer possible, but it has returned. And so that makes RSA, and in particular, static private keys, vulnerable. Another thing is quantum computing. I will discuss this only for a couple of slides. Quantum computing can be used to factor prime numbers very, very rapidly. Let me leave it at that, basically. It is progressing quite rapidly, and prime number factorization is the basis of RSA. What happened is that Peter Shor, an MIT math professor, came up with an algorithm to factor large prime numbers. Again, the basis of RSA. People thought that could be done only by brute force, but he came up with an algorithm. But the problem is that algorithm required a quantum computer, which he did not have. So then, when Isaac Chang came up with a quantum computer and managed to factor the prime number 15, or the number 15 into its two prime factors, 5 and 3, this was a great enhancement, but he could not scale it. So then that has been the story of quantum computing since. And you can see in the early days, we're talking about qubits, which is the measure of the power of a quantum computer. We're talking about 8 qubits, 10 qubits, and so on. And then some other interesting formulas, such as minimization, as well as Shor's algorithm. Now you come to IBM. And what IBM is doing is making a huge investment in quantum computing. And you can see they're talking about in 2023, over 1,000 qubits moving along quite rapidly to 4,000, 10,000 qubits. And imagine to yourself if IBM and Google, who is stepping into this, are doing it, many other people are also. So, but we don't even need a quantum computer to steal RSA public keys or private keys. Remember, these are static keys. What a static key is something that does not change. And so what people did was, well, why do we have to go to the trouble of inventing a quantum computer? That sounds like a lot of work and money. Why don't we just steal it? All right. So this is one of the things that came out from the whole debacle with NSA monitoring us, and that whole arena where things were made public. And you can see this article which came out. And this is an article from, there was a GCHQ presentation where they talked about where the keys are for a great many cell phones. And the keys are on the SIM card, and they are protected. And they can also be stolen. And that is what came out, is that the keys were stolen, and thus people were able to see the data. And again, I'm not taking a position one way or the other on some of this. Certainly, governments need to protect people against terrorists and other attacks. So it's not a clear-cut question of which side is right. Again, I come back to the armed conflict arena. We need to figure out a solution where everyone can live cooperatively and do the job they need. I do not actually have much hope for this. But the reality of today is that for doing network diagnostics, many people use exactly this. They use long-term RSA static private keys, and you save them and you put them into your out-of-band decryption devices. Let's say it's a Gigamon device, or it's a Palo Alto firewall, intelligent firewall, IDS, even Wireshark. You need that static private key to decrypt the data. And who are these enterprises that I'm talking about? Well, these are the top 10 companies on the Fortune 500. Oops, sorry about that. We also have healthcare, government, schools. Everybody needs to manage their networks. And by and large, this is what many people, if not most, are doing. And so how do they solve problems? What they do is two things. If it's very hard, you have to actually decrypt the packet. That means you have to see what people are seeing inside. And I'll walk through some of that with you. Also, you need to do, that's your deep packet inspection will come into that area itself. This is done by intelligent firewalls, IPS devices, and the like. And so let's look at what I'm talking about. So let's look at a TLS 1.2 session to Google. And you can see over to the side, the client hello, at server hello, starting the session, and all the stuff that you see, which is called application data, is all encrypted. You can't see what's in the packet. Of course you can't, but let's say that there's a problem with the application and you're going to the wrong site. Well, you can't see that either. The other thing that TLS 1.2 does, it sends a great deal of the certificate in the clear. So you can see how much good information is in that certificate. You can see who the certificate comes from Google, who's the authority, the certificate authority, it's Google, and so on. In TLS 1.3, all of this is encrypted, and also only the endpoint has the private key. So if there's a certificate problem, none of your middle boxes can see what that problem is. I'm not even talking about decryption. I'm talking about handshake. So what do you actually do when you want to decrypt TLS data? For example, this is in Wireshark. And Wireshark, you can go in and say, this is for TLS, and I'm going to create a pre-master secret log file. And many programs, I mean, many like browsers, Chrome or Firefox will do this for you. You can set an environment variable in Windows to create the SSL keylog file. One of the things it contains in it is the client random, and then the pre-master secret. And then voila, when you put that in, now you can see exactly what is in the packet. As you might imagine, if you need to do diagnostics, this is extremely helpful. In fact, unless you've got a very minor kind of problem, it often becomes difficult without decryption to solve difficult problems. And again, I'll walk through a little bit of why that might be. Notice here, this is the decryption feature from one product, Gigamon. I'm just picking on them as an example. There are many others. And notice that if you want to decrypt, you need to use the public key and provide that for them. And this is the RSA key. You might wonder why this all came about. And part of it, again, is there is a conflict, another conflict at the IETF, which is the end-to-end principle. What that says is that we should have smart endpoints and dumb networks. And some people feel that is the only way to have good networks. And this is literally a conversation with someone in the leadership that I had. And others believe that that is completely unsustainable, that you create more and more complex endpoints and network functions, and middle boxes have very useful functions, load balancers and so on. Again, I will go back to my market analogy. If there is a middle box, say a firewall, load balancer, and so on, if they cannot sell it to people, it will quickly disappear and go out of the market. So if it does exist, it means there is a market for it. It serves a useful function. So you have to learn to live with it. And if you create a situation where the middle boxes cannot do their job, again, they are not likely to take going out of business with much joy. In fact, they will likely not do it. So another problem we have is that in the West, and I'll say in particular the United States and Western Europe, we started computerizing very early in the early 60s and 70s. And what was done first was the core business functions. And for example, drilling an oil well. I used to work for a long time for a very large oil company. And it was to dig a well, an exploratory well, was at that time $1 million or so. And one wishes not to dig many dry wells where there is no oil. It is wasted money. And so algorithms to figure out where there is a good probability of oil and so on are probably likely to be the first things to be computerized, or for example, payroll, some of those things. And this, I will say, is first mover disadvantage, because much of this, many of these applications are quite old. And the attitude is, if it ain't broke, don't fix it. This is, again, a conversation that I had with somebody at a major US government agency. And this was about actually transitioning their application to a different protocol. It actually happened to be IPv6. And he said, listen to me, our core application was written in the 70s. And if you think I'm about to rewrite that when it works perfectly well to support IPv6, you're just wrong. And so what happens then is we have ossification at the application layer, which makes it difficult to come to newer versions and newer, more secure versions of the protocol. Let me tell you about something else, which leads to why we may need sophisticated debugging techniques and why decryption is done at all. Okay, so let's imagine that we have a program, and the program has 100 bugs. Let's say it's going to take 100 units to find and fix everything. Well, if you are developers at all, you will know that the first that some bugs are very easy to find, very repeatable. You know, you maybe can't even start up the program, it crashes immediately. You're going to fix that very, very quickly. So the first 70 bugs might take maybe 40 units of effort. That after that, you get something a little more complicated. So those next 20 need 30 units. After that, the last 10 bugs, they may show up only when intermittently, or only when you reach a certain scale. And it is quite difficult. It takes quite a bit of work to find those. And as a software developer for many, many years, I can tell you that many companies fix only 70 to 90% before shipping. I remember sitting there with the QA team on one side and the project manager on the other side, and they're saying, we have customers you need to ship. And we're like, okay, well, here goes. And you know, software is embedded in everything. And by everything, I mean network devices, routers, firewalls, operating systems, PCI cards. There's software everywhere. And imagine that all these people are shipping with things that still have potential bugs. Your applications have potential bugs. So let us think about solving problems on networks. Now, this is Nalini's analogy of network problem. So imagine that if you have 100 problems, and so you will take an increasing amount of effort. So the first 70, let's say, are quite easy. In fact, for the first 70, probably the only thing you need to ask is, what was the last thing you changed? Back it out. And then you're bingo, you're all set. Then you can solve that problem over time. And then we need more and more effort to solve problems, because, as I say, you're working with flawed software in all your network. People are shipping flawed software, and some of these bugs may show themselves only at scale. And oftentimes what you need to do is decrypt. This is where we come back to the whole RSA and encryption analogy. I mean, a problem. This is why we need to encrypt. You will see that much of the core data is stored in IBM mainframes. IBM mainframes will allow you to decrypt TLS 1.3 at the endpoint only. You're not going to see what's going on in the middle, where that may be exactly where the problem is. The other thing is many ISPs use a part of the what is in the TLS handshake called server name indicator to filter websites. Well, they are not, their ISPs are in the middle. That's your telephone company or internet provider. They can't do it at the end point. They don't own the end point. And so this makes it very difficult for them. So let's now move to DNS over HTTPS. I had a conversation with somebody, a very, very large enterprise, one of our top 50, and telling him that with DNS over HTTPS, the browser itself will have a pointer to do DNS. And he said, what? You mean DNS is going to be resolved somewhere not in my enterprise? I'm like, that's the idea. And so whoever sees it sees what sites my company goes to and what the pattern of behavior is for my company. Yep. And so he said, how do I change this? And I will tell you that actually some of the browser vendors have been very, very cooperative, and they have changed it so that you can make those changes yourself. And I think really people should be running DOH servers internally. But as I say, I will say some companies have been very, very cooperative with this problem. And this is an interesting a little highlight. When this all was in its heyday, when these fights were being had, a question was even asked in the parliament about the IETF's DNS over HTTPS protocol. Yeah, it would be interesting to see what the answer was. So let's talk a minute about QUIC. QUIC is, as I said before, it's a new transport layer equivalent to TCP or UDP. The idea is it's a faster way to do HTTP and HTTPS. It is moving very, very rapidly. many large tech companies, at least, are implementing Quick. Google, Facebook. If you do packet traces, just trace in the wild, you see a great deal of Quick traffic. It was originally developed at Google, and now it is an IETF standard. And I'm not saying they're wrong to develop a new transport protocol. The problem is that there is ossification at the transport layer protocol level. What happens is a lot of middle boxes, firewalls, and the like will drop packets unless they're TCP or UDP. You have NATs, which are rewriting options. If you can't really add other new options in TCP, it just doesn't work. And the reason you need options and so forth is the protocol needs to evolve. You can't just keep on using a protocol that was developed in the 80s and 90s without any change. There are new things that need to be done. This creates ossification. And so we need a new protocol. It becomes it becomes a very difficult battle here, because again, if the battle to allow Quick through the transport layer is done by having Quick run under UDP, but it's essentially a transport protocol. It's very difficult to modify TCP. The other thing is something called TLS fingerprinting, and this is just an email that I copied from the TLS IETF list. And what they say essentially is that the protocol is being defined by the implementation. That is, there is so much of the protocol out there and so many middle boxes, quote unquote, playing with the various portions of the protocol that it becomes very difficult to change. This is difficult, and that's why for Quick, what they have done is hidden everything. You can hardly see any of the data. So then if they need to change it, it can happen. But what happens then is when you do all of these things, and the speed of development is that many large enterprises resist adopting these new protocols because not enough accommodation has been done to their needs. And frankly, I will blame the enterprises too. Not enough enterprises come to the IETF and voice their opinions where many of these changes are coming about. What is really needed, other than collaboration and trying to see other people's point of view, which I have completely given up on, is good ability to transition between protocols. And I'm talking about for the large enterprises. The Google and Facebook, the internet companies, they will take care of themselves. And let's think about where we're going too. If we're thinking about internet standards and the world that it's changing, when we're building standards, we're building them for the world that will be 4 or 5 years from now. And this is an interesting article or interesting segment about how the future is already here. It's just not evenly distributed. For example, here's an example of a chip that is embedded in your brain. And what it will do is it will store your memories. Imagine this can be very, very useful for people who have Alzheimer's, is you can have access to your memories back. But the problem, of course, is who will have access to these memories, and what if you can download someone else's, and will this be protected with TLS? Interesting, right? So questions, thoughts? Would love to have get your opinion on what you've heard.
Thank you very much, Nini. I'll just open up the lines now. If anybody wants to ask a question, you can unmute yourself, or you can put the question in the chat. Well, we've had a few thanks, but no questions.
Great. So thanks so much for the opportunity, and you have my email, and if you please feel free to contact me if you would like.
Thank you very much, Nini. Okay.
Thanks for the opportunity.
We're going to close the call now.
Thanks for the opportunity, Neil. Bye.
You're welcome. Thank you.
Bye.
Bye, everybody.